Last lecture we have seen the last few theorems on properties of continuous function. Rolle's theorem, Lagrange's mean value theorem, Cauchy's mean value theorem, they are very important results and are required to use many times while problem solving. Okay, so now using those theorems, today's job is to prove L'Hopital and look at how it works. So let me straight away write down the statement of the theorem. Let f comma g be on defined on a comma b to r. Let f of a is equal to g of a is equal to 0. First we will do with 0 upon 0 type of L'Hopital. We understand the nitty-gritties of the proof of, then we will also write proof for infinity upon infinity, and we will say that similarly different proofs also can be read. Let g of x is not equal to 0 for every x belonging to a comma b. If f comma g are differentiable at x is equal to a, and if g dash of a is not equal to 0, then limit as x tends to a plus f of x upon g of x is equal to f dash of a upon g dash at a. This is what is a technical statement of the theorem, where the condition is f and g are differentiable at x is equal to a. So this is a restriction. This is something which, if we can eliminate, it will be good. But presently, because this is first result, if it is differentiable, then what kind of proof we can write for this result, this theorem? And it is easy. Therefore, I give you sufficient time to write your own proof, because it is easy. Let us write the proof. It is absolutely simple. Proof. What is given? Given limit x tends to a plus f of x upon g of x. That is what we are supposed to, we are supposed to start with LHS. This is what we want to find out, and we are supposed to reach towards derivative in the numerator and derivative in the denominator. So we have to have in mind what is the definition of derivative of f of x at a. So we have to move in that direction. This is equal to limit x tends to a plus f of x minus f of a. Because f of a is given to be 0, we don't mind subtracting from numerator. We don't mind subtracting from denominator. Is that right? That will not change value. Now if x is tending to a plus and therefore x is not equal to a plus, so I can always divide. Limit x tends to a plus f of x minus f of a upon x minus a all divided by g of x minus g of a upon x minus. I can always do this. Because f is given to be differentiable, g is going to be differentiable. Therefore, the next step is I can split the limit. Limit x tends to a plus f of x minus f of a upon x minus a into 1 upon limit g of x minus g of a upon x minus a as x tends to a plus. We can always write this. Then we can say that this is by definition and differentiability of function which is given f dash of a, and this is by definition g dash of a by definition, right? Hence proved. So it is a very simplistic proof. So now let me give you an example where you can find out. Suppose limit x tends to example 0 plus sin x upon root x. Find out. Okay, almost all of you, I'm recording, almost all of you have shown me the answer 0. Maybe the answer is correct, but then there is something wrong with your answer. Maybe answer is still correct, numerical answer, I have to give full marks, but then something is wrong. Find out what is wrong. Now the flaw is that the given function sin x upon root x, if we consider sin x as f of x and root x as g of x, then the prerequisite of our theorem is in trouble. Prerequisite of our theorem is f and g are differentiable at x is equal to a. And you will find that root x is not differentiable at x is equal to 0. Therefore, you are violating the condition which is required for the theorem to be true. But then answer is true. Therefore, maybe what we can say is that is what I was saying, that this is a very condition. That is very strong condition, and we will be very happy if we don't have that condition. Suppose I this sentence. Suppose I eliminate this sentence from then you will not be in trouble. But then this proof is not going to work because you simply are having the derivative which happens to be equal to 0 because function is not differentiable. So you just do not know what is to be put in the denominator. So you will win. So the situation is the result is true, but the root is wrong. Eventual L'Hopital is applicable to this function. Eventually the limit is going to be equal to 0. But then this theorem and its corresponding proof is not sufficient for solving this limit. And therefore, this proof of L'Hopital, even if it is simple, very easy to write. I mean, there was nothing, this was just algebraic manipulation. It is not going to help us. I mean, the proof is wrong, result is correct. and we have to make the rule more versatile, not so rigid. Therefore, it is our job to write down the theorem statement again and get into the proof, different proof, which will survive for difficult situations like this, where differentiability is in question. Okay, no problem. That is what is actually your L'Hopital rule number 1. Let me put it at 56%. Yes. L'Hopital. I want it to be green. Yes. L apostrophe L'Hopital rule 1. Statement. Now this is what is the most common type which we are dealing right now. 0 upon 0. We will see what we can do with other types. We have 7 indeterminate forms. This is the most common, therefore we are writing it for this. Let f comma g, they are defined from open interval a comma b to r. 1. Let f comma g be differentiable over a comma b. 2. Let p of x is not equal to 0 for every x belonging to open interval a comma b. Right. 3. Let g dash of x is not equal to 0 for every x belonging to a comma b. 4. Limit as x tends to a plus f of x is equal to 0. 5. Limit g of x, limit as x tends to a plus g of x is equal to 0. Then what is going to happen? Then if 6 limit x tends to a plus f dash of x upon हे काय लिहिलं मी then and if then खोडा 6 if limit f dash of x upon g dash of x equal to L, then 7 limit x tends to a plus f of x upon g of x is equal to L. This is complete correct statement of L'Hopital rule number 1. Now I give you sufficient time, as much as you want, to decode the proof of this theorem. Okay, let me give you a hint. We are supposed to use previously proved theorem, which is Cauchy's mean value theorem. Quashes mean value theorem will get you through this particular proof. try to use it. That is what is your hint.
सर पण इथे ओपन इंटरव्हल असल्यामुळे ए च्या इथे काहीच डिफाईन नाहीये ना.
आणि हिंट देऊन झाले, आता तुम्ही तुमची बुद्धी वापरून काम करायचं. Okay, let us write the proof. Now, as I said, the hint is we have to apply Cauchy's mean value theorem. So we need to know what are the prerequisites of Cauchy's mean value theorem. The prerequisites are simple. Functions f and g must be continuous on closed interval a comma b and differentiable on open interval a comma b. Then there exists c belonging to open interval a comma b such that f of a minus f of b upon g of a minus g of b is equal to f dash of c upon g dash of c, where c belongs to open interval a comma b. That is what is our statement of Cauchy's mean value theorem. Everything is available for f and g in the prerequisite over here. However, the entire theorem talks about open interval a comma b, and Cauchy's requirement is the function must be continuous in closed interval a comma b. Now, when x tends to a plus, f of x tends to 0. When x tends to a plus, g of x also tends to 0. And we don't have any alternative but to use Cauchy's. Therefore, first thing that we need to do in proof, define f of a equal to 0 and g of a equal to 0. That is what we do from our pocket. I mean, we do not know how f is behaving at a or how g is behaving at a, but we only know that as x tends to a plus near a, the value of the function becomes 0. So there is no harm in defining f of a is equal to 0 and g of a is equal to 0, right? Therefore, now what we are saying is limit as x tends to a plus is 0 and f of a is 0. This implies f is continuous at x is equal to a and g is continuous at x is equal to a. Now statement 1 says f and g are differentiable over a comma b, therefore they are continuous over open interval a comma b, and now we have said that they are continuous at a. So 1 and these two statements, 1 and above, imply f comma g are continuous over definitely closed interval a comma b. We are not interested in b because it is far away from a. We are trying to prove this theorem near a, right? So this is one good thing that we have done. And now, hence what we can say is consider interval a comma x where a is less than x is b, right? X is any point between a and b, and it is differentiable at that point, therefore it is going to be continuous also, therefore now I can have both the brackets closed interval, right? Applying Cauchy's mean value theorem, CMVT, over closed interval a comma x, we have for epsilon, नाही, CMVT काय सांगतो, एप्सिलॉनचा काही संबंध नाही. CMVT says f of x minus f of a upon g of x minus g of a is equal to f dash of c upon g dash of c. Applying we have काढून टाकू, applying CMVT over a comma x, we get there exists c belonging to open interval a comma x such that this is what is your statement of CMVT. Okay, what is the meaning of this statement, continuity at A? Let us write down the meaning of continuity at A. Meaning of star. Star implies for every epsilon greater than 0, there exists delta greater than 0 such that for every x belonging to delta neighborhood of A, intersection a comma x, we have what do we have here, star and I mean थांबा जरा, आता मी काय लिहितोय, कंटिन्युटी तर झाली त्यामुळे CMVT झाला, आता स्टार नाही, सॉरी, स्टार anyway we have used for applying CMVT, so star is not implying this, but the given condition 6, condition number 6 is implying so. Condition number 6 says limit as x tends to a f dash of x upon g dash of x is equal to L. What do we mean by 6? We mean for every epsilon greater than 0 there exists delta greater than 0 such that for every x belonging to delta neighborhood of a intersection a comma x, the interval under consideration, we have L minus epsilon is less than dash of x upon g dash of x is less than L plus epsilon. It is going to happen for every x between okay, let me write down that explicitly. Above statement is true, this is true for every x, Shiva. This is true for every belonging to a comma a plus delta. Is that right? This implies L minus epsilon is less than f dash of c upon g dash of c is less than L plus epsilon as c belongs to a comma x. What is this c? This fellow. This fellow is our c. Is this correct? Yes. Up to this point it is correct. And after that, now because this is true and this is true, maybe we should name them, but it is okay now. Let me call this as some this star. This star implies L minus epsilon is less than f of x minus f of a upon g of x minus g of a is less than L plus epsilon. Is that correct? Yes. Therefore, this implies now f of a and g of a, both of them are 0. L minus epsilon is less than f of x upon g of x is than L plus epsilon. Therefore, by definition, limit as x tends to a plus f of x upon g of x is equal to, okay, I made this complete proof available on the board. Go through it several times, check whether you have really understood it or not, find out if there is any flaw in this proof, and if required we can explain. I can explain it to you again, but copy it properly first. Now I would like to make a comment here that exactly same proof. See how many variations are going to be there in this as far as L'Hopital is concerned, because for every different condition we have to have a proof, right? So let me just tell you what is going to be the,
सर
yes.
सर पण या ह्याच्यात पण ती कंडिशन गेलीच नाही ना की एफ एफ ऑफ एक्स अँड जी ऑफ एक्स हॅव टू बी डिफरन्शिएबल.
ती कंडिशन आता लागत बायपासच झाली ना ती कंडिशन. फक्त कंटिन्युटी पाहिजे आपल्याला, ती डिफाईन केली आपण. डिफरन्शिएबिलिटी तिथे नसली तरी चालेल, तरी सुद्धा प्रूव्ह होत आहे.
सर पण ते पहिल्या कंडिशन मध्ये लिहिलेलं आहे.
Okay. Now, the variation in this is going to be in 6. In 6, the limit is becoming L, therefore the limit of f of x upon g of x is L. But if this limit was plus infinity, then the resultant also would be plus infinity, and exactly same proof will not work. We will have to change the proof as per the definition of limit when it tends to plus infinity. That capital M, given capital M, you produce a limit f of x greater than that. That kind of proof will be there here. It will not be L minus epsilon, L plus epsilon. Okay. And if there is one more variation that it goes to minus infinity, then this is also going to go to minus infinity. In that case, the limit definition says you give me a number, I give you a smaller number than that. That kind of proof will be there. Otherwise, the first part of proof is going to remain same. Application of CMVT is going to remain same. So basically 0 upon 0, there are 3 sub proofs. One when it is L, one when it is plus infinity, one when it is minus infinity. So we have written one out of it. Now what we are going to write is L'Hopital for infinity upon infinity. So let me write down the statement of the theorem and give you sufficient time to think about it. It is little involved, but you have to try your level best. After that, I will write the proof. Statement of the theorem. L'Hopital rule number. Let Okay. So only difference is these limits are not 0 0 now, they are plus infinity plus infinity. In that case, your limit f of x upon g of x is also going to be L. This is L, L. Now again, there will be two more variants in this, plus infinity, minus infinity, and it is just the change in the definition of the limit. That is how we are supposed to complete that proof. So we are not writing those proofs. Also, we will write only this proof for L and L. However, the type is infinity upon plus infinity. Okay. Now I give you sufficient time to think. Okay, the difference in this rule and earlier rule is very clear that it is as extends to a, the functions are tending to positive infinity. Functions are tending to positive infinity, that means they are not bounded, they are unbounded, and as you go near a, they are going to positive infinity. So practically the curve, say if I don't want to draw fx and say it is open interval, so this is hollow circle a. At this point, if I draw dotted line, then f is going to go asymptotic as you go near a. Same will be the case with g. Okay, so we will have to deal with this kind of situation, and there is a trick. I mean, the proof that I am going to discuss now, I will not claim that it is completely correct or technically completely correct proof, but we will write the proof which we will understand how it is working, and of course there will be some assumptions which we will be able to do, otherwise the length of the proof becomes very very long. I mean, therefore we will keep it crisp and short, but we are not just assuming everything to be true without proving it. So let us begin with the proof. Let epsilon greater than 0 be given. What is meaning of statement number 5? Statement number 5 implies there exists a delta 1 greater than 0 such that for every c, I will call that as c now because I want to use x for some other purpose. So for every c belonging to a comma a plus delta 1 and a plus delta 1 is less than b. I am not just crossing the interval and going somewhere out. Delta 1 is definitely, a plus delta 1 is definitely between a and b. We have L minus epsilon is less than f dash of c upon g dash of c is less than L plus epsilon. Okay, use this letter C very wisely here, but we have to understand that practically you can choose any point between a to a plus delta 1 and you will have this result. So C is chosen such that it is a point between a to a plus delta 1 and this result is going to be true because of phi. Is that right? Because of phi. So now we have got interval a to a plus delta 1 and we are supposed to create a situation for CMVT in the interval a comma a plus delta 1. So choose x comma beta belonging to a comma a plus delta 1 such that a is less than x is less than beta is less than a plus delta 1. In that sequence, note f and g are continuous over closed interval x comma beta. F and g are differentiable over open interval x comma beta. Hence, CMVT can be applied. Which implies there exists C belonging to x comma beta such that f of x minus f of beta upon g of x minus g of beta is equal to f dash of c upon g dash of c. Now, this c is a point or maybe a couple of points where this relation is being satisfied. But where that c is between x and beta. However, where are these x and betas? They are between a to a plus delta. Is this result true by limit definition between a to a plus delta 1? Yes. So therefore, is this C satisfying this requirement? Yes. This is very important that you understand. Therefore, now I can practically replace this by this in star. Therefore, this implies, but still job is not over. Still, this implies, star implies L minus epsilon is less than f of x minus f of beta upon g of x minus g of beta is less than L plus epsilon. Okay. Now, in earlier proof, this fellow was 0, this fellow was 0, but now they are not 0, therefore we cannot eliminate them and just directly write down f of x upon g of x. So we need to do little more work. And the work is as follows. This implies its algebra. L minus epsilon is less than f of x inside bracket 1 minus f of b upon f of x. Take out f of x common in the numerator. G of x inside bracket 1 minus f of b upon, g of beta upon f of beta, bracket closed, less than L plus epsilon. Now, am I allowed to do this step? Because actually I am dividing by f of x and g of x. Actually, I am dividing by f of x and g of x. F of x and g of x. Yes, as f of x and g of x are never 0. I think that is what we have written in the prerequisite. They are never 0. G of x and g of it. If it is not written, then we will have to do something about it. Okay, we will do something about it, because if suddenly f of x and g of x become 0, then this step is illegal. So let me explain what do we do. It is not given. So we wish to do this. So what remains to prove is, let me write down, is true if f of x and g of x are never not equal to 0. Okay, so this I am keeping it pending right now. Unless I prove this, I will not be able to write down this step. But if this step is true, if this is true, note as tends to a plus, f of x tends to plus infinity, and as x tends to a plus, g of x also tends to plus infinity, right? Therefore 1 minus f of, okay, b is a finite point. Okay, let me write down that also. Note, b is a point in the delta 1 neighborhood, or maybe b is a point belonging to a comma a plus delta 1, implies f of b is finite. Okay, why is this true? Because at a the function is going to plus infinity. At a function is becoming positive infinity. This is your a, and you are choosing, suppose this is your delta 1, choosing b, which is beta, between a and a plus delta 1. Therefore if the function is becoming plus, is tending to plus infinity at a, in the delta neighborhood of a, delta 1 neighborhood of a, it will have some value. It will have some value, right? Therefore f of beta is finite. Similarly, g of beta is finite. Also both of them are positive. Also note that both are positive. This implies 1 minus f of b upon f of x and 1 minus g of b upon g of x will be equal to 1 in limiting case. Okay, let me complete and then you can ask questions. So therefore, this equation, which I will call star implies limit L minus epsilon is less than f of x upon g of x is less than L plus epsilon, implies by definition 6, 7. by definition, limit x tends to a plus f of x upon g of x is equal to a. Okay, so now this is not complete because I am yet to talk about this. Why will f of x and g of x be not equal to 0? We will think about it. Hmm. Now this graph explains that. If near a, the function f of x is going to plus infinity, function g of x is also going to plus infinity, then of course you will be able to find out x, because x is between a comma a plus delta. You will be able to find out x where it is positive and is not equal to 0. Okay, so that is what x we are going to consider eventually. X is dynamic, x is moving. Understand this situation. I mean, we will write it in a formal way, but this is the situation which is happening. Let me explain you by drawing diagram. This is open interval a where function is becoming asymptotic. It is going to plus infinity. This is your a. Let us say this is your delta 1, a plus delta 1, not delta 1, this is a plus delta 1, this point, and b is somewhere here, b, somewhere here. Now you are choosing x and beta, okay, and x is moving towards plus infinity. That is what is our condition. X is moving towards plus infinity, b is always a fixed point, b is a point between this and you have fixed it. Now you can always fix b because the graph is always going to be like this, always going to be like this, and even if after beta it is going towards say negative side, you of course have some space for adjusting your b to be positive, and x is to the left of b, and x is dynamic. X is moving from here to here. X cannot go to the left of A, X cannot go to the right of B. X is moving in between. And beta is definitely a fixed point which you can choose, where f of beta or g of beta is not equal to 0 and it is a positive number, right? So from beta to A, from beta to a, you are choosing x in between, and we can ensure that the function x is not going below x-axis. Suppose you say that the function is like this. Function is like this. What will happen? Then in that case, you should choose this as beta. After that, it is positive. If it takes one more wave, you choose the next one. So eventually the function has to go to plus. Therefore, you will find some delta neighborhood. Maybe we can call it as delta 2, delta 3, delta 4. And then you finally choose the delta which is the minimum amongst all. That is what is actually the formal proof of this result. You keep on choosing deltas. But what I am trying to explain you right now is, if the function is asymptotic at A and it is taking say different values, and suppose it is going, we don't know where it is going after b, this is b, this is a, open interval a, then if you choose this beta, then of course there are a couple of points before beta where it can become 0. Will you be able to find out a point where between a to beta the function is never 0? Yes, you will be able to find out that point always, because eventually a differentiable function is asymptotic at a and it is tending to plus infinity. Therefore, you will always be able to zoom this. Maybe I can zoom it now like this. You can zoom it, you can pan it, and say that now I am not worried about what is happening after b towards what is happening after B towards this side. I am worried about this beta, and any x between A to beta where it is not equal to 0. That makes us comfortable as far as this step is concerned. As far as which step is concerned? This is concerned. It is fixed, positive, and finite. This is then going to be our correct step, and also this is going to be our correct step. We are not dividing by something which is 0. Okay. So because it is a video recording, I leave it to this point. I am not making the proof more difficult by writing all that what we have discussed, and keep it at this stage. So if this is true, then the final result is true. And maybe what if we really have to write the rigorous proof of these two conditions to be true, we will have to choose couple of more deltas. And finally, write down the proof for the smallest delta. I think we have chosen one delta somewhere in this proof. This is delta 1. Maybe we will have, see in this diagram, if suppose this is your delta 1, in this diagram, if suppose this is your delta 1, then delta 1 is not choice. You will have to have delta 3 or delta 4, which is going to be your correct choice. Minimum between them you have to choose, and then complete this x comma beta proof for A to delta 3 or maybe delta 4 or delta 6. Okay, but the essence of this proof is to convert the Cauchy's mean value theorem into the definition of limit. That is why the Cauchy's mean value theorem is extremely important and useful. Now the variants of this L'Hopital 2 will fall in place because they are just different definitions of limits we have to use to prove them. Okay, I think I have explained whatever I want to explain. If you have any questions, you can ask. Otherwise, copy this and keep it in your notebook. I was just searching on internet at what level these proofs are taught in the mathematics course, and I got some replies in Quora, etc., that it is calculus 1 or calculus 2, it is after 12th. In worldwide, these are taught, maybe for us in BSc second year it is taught. Maybe I don't know whether it is taught with this rigor or not, but I think if we are teaching it to 11th standard student and if they are understanding what is happening, it is an achievement. Okay, so write down the proof, think about it, check whether you have understood. Any doubt at any step, you ask me, I will explain it again.